We'll go back to a symmetrical fault. For fault analysis from this point, we will be considering all three sequence networks here as we can see. We will only have different interconnections for these sequence networks for varying types of fault. For a three-phase fault, only the positive sequence network is considered. Solving for the sequence currents in this fault, the positive sequence current may be solved using the first equation, and the negative and zero sequence currents are equal to 0. With this, we now have all three sequence currents, but this does not directly represent the actual current flow in the faulted system. We need to convert these sequence currents to phase currents. Applying that in the previous sample problem, where we solved for the Thevenin equivalent of sequence networks, we are asked here to calculate the per unit subtransient currents in phases A, B, and C for bolted 3-phase to ground short circuit at bus 2. These are the Thevenin equivalents of the positive sequence network, negative sequence network, and zero sequence network that we solved earlier. First step in finding the phase currents during fault is to solve for the sequence currents. Solving for the positive sequence current with this equation, and using the pre-fault voltage of 1.05 angle 0 degree that is given in the problem, we will get a positive sequence current of negative J 7.5594. Zero and negative sequence currents are always zero for symmetrical faults. Then we'll use this equation to convert the sequence currents to phase currents. And these are our phase currents. It can be observed that they have the same magnitude across three phases, but are out of phase by 120 degrees. And this is expected for asymmetrical fault. In our prior discussions, we're only solving for current at phase A since we can easily get the other two. But for unsymmetrical faults, with it having different currents per phase, then we need to determine all three phase currents.